All right, so in this video, we are going to look at some examples or an example of finding absolute extreme on the closed interval. So last time we developed sort of all of the kind of logic and thinking that goes behind the extreme value theorem and then where those extreme values actually occur. And all this leads to our test for absolute extrema on a closed interval. So first, you have to have a continuous function on the closed interval. That's the extreme value theorem part that guarantees we actually have absolute extrema. Then our observations kind of tell us that those absolute extrema will occur either at critical points, so we find the critical points, or at the endpoints. And that's why on step 2, we plug in the critical numbers along with the endpoints back into the original function. And then we're just going to say whichever one's the biggest, that's the absolute max, and whichever one's the smallest, that's the absolute min. So we're going to be doing algebraically what your eyes kind of naturally do on something like 3 or 4. Your eyes naturally look at, oh, the peaks and the valleys, where f prime's equal to 0 or doesn't exist. And then you kind of naturally look at the endpoints, and you're just visually naturally comparing where's the biggest, where's the smallest, peaks, valleys, endpoints, looking at where they're at on that function. And so that's what we're going to do algebraically. So first, take a look at this example. F of x is equal to x times the square root of 1 minus x squared on the closed interval from -1 to 1. So the first thing that I want you just to observe is the domain. So kind of in parentheses here to start, I just want us to note the domain of f. So the domain of f is going to be, since we have a square root, we need to keep everything underneath of a square root greater than or equal to 0. Well, this is going to lead us to two numbers, plus and minus 1. I mean, you could think about maybe factoring that into the difference of two squares, 1 plus x and 1 minus x. And so at 1 and -1, those are the two locations that function 1 minus x squared would equal 0. And so you can't any longer say, like 1 greater than or equal to x, or add the x over. When you have a polynomial inequality like this, the only thing you do is you find the places where it would equal 0, and then you think about just looking at those and what their signs would be if you subbed in some numbers. And obviously we can also look at the graphing calculator, but this is kind of how we would look at solving a polynomial inequality by hand. And so we would sub in some value, like let's say x equals -2. And this is going to be a process that we're going to use later on. So it's kind of a nice thing to see here a little bit as well. So if you sub -2 into the 1 minus x squared, that would be 1 minus 4. 1 minus 4 would be -3. That would be negative. And what we would know is the square root of negative does not exist there. Now, if you subbed in something in between, so if you subbed in something like 0, you would have 1 minus 0. That's 1 that is greater than or equal to 0. And then if you subbed in something bigger than 1, like 2, and then you'd have, again, 1 minus 4, that would be negative. So we need where it is positive. So we're interested in where it is. In order to be defined, we want where it's greater than or equal to 0. And so these are all of the values that would be in the domain of f. So the domain of f then, kind of bringing this back, our domain of f is everything from -1 to 1. So that's really the interval that was given. So it is a condition of this theorem to apply the extreme value theorem that we have to be continuous on this closed interval. And we are, that's the domain. We could also look at the graph of the function, which we'll probably do maybe a little bit later here. Okay, so we're just kind of verifying that we are, continuous on this closed interval from -1 to 1. So I'll just say check. All right, so because we have met that criteria, right? So this was our criteria, continuous on this closed interval. So we were continuous on this closed interval. Now let's actually apply our steps for finding the absolute extrema on a closed interval. All right, so what are we going to do? We're going to need to find the derivative. So the first thing we're going to have to think of here in terms of f is we're going to have to make sure we realize that we're working under the outermost rule here being our product rule. And so we're looking for f prime so that we can find the critical points. So we have our first one left alone, x times the derivative of the second factor is going to be 1/2, 1 minus x squared to the 1/2 minus 1, so to the negative 1/2, and then times the negative 2x, derivative of the inside, plus changing that order, so the second factor, so that square root function left alone, and then times the derivative of x, which is 1. All right, so initially there's maybe not a whole lot of like quick and easy simplifying other than maybe the 1/2 and the 2. Other than that, nothing super fast. So we are going to have to work with this, right? So in the last chapter, I would say like, let's work on our simplifying because there's going to be a lot of times coming up where we're going to have to be able to do this algebra. And this is where this is occurring. We have to be able to set this equal to 0 and solve. So we really need to clean this up. So probably the first thing I would say is let's take this first term, and where we have a negative exponent, one of the first things I'd encourage you to do is kind of rewrite that with a positive exponent. So move that binomial to the negative 1/2 into the denominator, and now it's to the positive 1/2. Okay, well, what does that leave you with in the numerator? Well, in terms of the monomial portions that are left, we have the negative, and then you have the x and the other x, so it looks like a negative x squared. All right, well, that already looks better, and I wouldn't even say we've done much simplifying there. I'd say all we've really done is just clean it up. So now, my advice would be to think about this second term as being over 1, and then let's go ahead and get a common denominator and actually add these two terms together. So I am going to multiply by a version of 1 here, 1 minus x squared to the 1/2, or if you prefer, at some point we can rewrite this as a square root. So we're going to multiply that second fraction so we can get a common denominator. So let's go ahead and do that. So in the first term, we have our negative x squared, and in the second term, I have a quantity to the 1/2 times another quantity to the 1/2, and so that's just going to leave us with that quantity to the first, or if you were thinking of radicals, it would be square root of a quantity times square root of a quantity is just going to be that quantity. And then this is all over our common denominator, which again, you can leave as the 1/2 power. You might rather look at it as a square root. And so now we really have a pretty decent form as we look at our derivative here. So combining like terms in the numerator, it looks like we have a minus 2x squared altogether. Since it's addition, I don't have anything in front of that binomial that potentially could have been requiring some distribution. We don't have that here. And so here's a nice simplified looking form of our derivative. All right, so now that we have a pretty decent form on our derivative there, we want to look for, what was the whole point here? Some algebra. That is part of the point. I'm doing something that requires maybe a little more algebra of you. But really we want to look for critical points. So we're looking for where f prime is equal to 0 and where f prime does not exist. And so, looking for where f prime is equal to 0, since we have a simplified fraction, and that's part of the reason I like to do some of that simplifying in advance, is then it makes this work a little bit easier. So a fraction goes to 0 when its numerator goes to 0. So if we just, little basic algebra here, add our 2x squared over to the right-hand side, and so we would now have our 1 equals 2x squared. And just continuing here, we'll divide by 2, and then we should be in a position where we're going to just need to get rid of the square. Now be careful, when you take a square root to get rid of a square, you have to remember to introduce that plus or minus square root on the other side. So it looks like we have x equals both plus and minus square root of 1/2, which is the same thing as square root of 1, which is 1, over square root of 2. Or if you prefer, that's a common one from your unit circle, rationalize the denominator and it's root 2 over 2. Either way. Now, where f prime does not exist, well, this would, be us looking for where the denominator goes to 0. And so where the square root of the 1 minus x squared goes to 0, square both sides, and you're looking at where 1 minus x squared goes to 0. Add the x squared, and you're looking at where 1 is equal to x squared. And again, hopefully you don't even need to write those kinds of steps out in between here. But the one, again, to just be a little bit cautious of is if you're taking the square root to get rid of a square, you do need the plus or minus square root on the other side. So it looks like we have two values here at both plus and minus 1. Now, FYI, these are all critical points. So by definition, what we had over here, those are critical points, as are plus and minus 1, because if you do f of plus and minus 1, those exist in your original function. So these, just so you're aware, these are all of our critical points. Okay, now, this wasn't just find the critical points though. This was the test for absolute extrema on the closed interval. So the last step is taking these critical points. So in our final step, what we're then doing is we are taking our critical points as well as the endpoints of your interval. Well, it just so happens in this case that the endpoints of your interval are essentially overlapping with, so this plus and minus 1 right here, it just so happens came out of where f prime didn't exist. It just so happens that those were, going back to the original up here, that these were the endpoints on your interval. So at -1 and 1. But I would say, make sure you realize that you are plugging in the endpoints of that interval. So be very, very kind of aware, I guess I would say, of that. All right, so in our final step here, we are plugging in the endpoints of the interval and the critical points here. All right, so the endpoints and the critical points. So we have the -1 over square root of 2, or root 2 over 2, and then +1 over the square root of 2. And keep in mind, these are obviously in between -1 and 1. If they weren't, then we wouldn't do this, right? So again, these were from the endpoints of your interval. So this is just very, very important that we're, being mindful of that. So make sure kind of as you go back here, let's highlight that these, even if they hadn't come out of where f prime did not exist, were coming from plugging in the endpoints of that closed interval. Okay, so as we plug these values in, back into our original function here, so the original function was x times the square root of 1 minus x squared. So if I sub in 1, I'm going to have, -1 times the square root of 1 minus -1 squared, right? So all these are being plugged back into the original function. So in this case, I'm going to, just in the interest of space, I'm going to erase some of this work. I don't need to see that kind of arithmetic work. So if you sub in -1, you're going to get 0. And then if you sub in, similarly, 1, that's going to make what's under the square root 0. And so that's also going to be 0. And then if we sub in, let's see, the 1 over the square root of 2, So what's that going to look like? This would be 1 over the square root of 2 times the square root of 1 minus 1 over the square root of 2 squared would just be a half. 1 minus a half would be a half. And then this is also 1 over root 2. And so 1 over root 2 times 1 over root 2 is actually just going to be a half. So at the end of the day, this is just going to be 1/2. Of course, you can use your calculator. And similarly, this will also multiply to a half, but the x term in front would have been negative 1 over root 2, so this one's going to have a negative carried along with it. All right, so after all of this, so in this final step of plugging all of these values into the original function, wherever you have the largest value, so this came out at 1/2, 1/2 is your absolute maximum. So that is your absolute max. And the smallest value of these four is negative 1/2, and that is your absolute minimum. So our final answer here is the absolute min is at negative 1/2, and the absolute max is 1/2. And so most of the time, if the homework asks you just like what is the absolute min or max, they're looking for that y value. If they say the xy ordered pair, well then obviously you have that there as well. All right, so let's just take a look at this function real quick, kind of pulling this together. I typed it into my y equals, but when you just maybe want to think about what is this looking like graphically, here's the original function. Let's just go to a quick zoom standard. And then that's very, very small, but it's enough for us to get a picture of what's going on with this one. So if we were to think about this graph, so what we sort of had, going on graphically. So if we were to, kind of think about the graph, okay, what we were looking at between -1 and 1 is, something that looks roughly like this. You can see the better, and I could zoom in and make that window a little better for us. But so what we had was kind of looking at these points, and we ended up seeing visually that this is where our absolute max was, and this was the absolute min. That's what we just found algebraically.